So welcome everyone to the Internet of Water Peer-to-Peer Network webinar series. And we have one of these every month. And today we have a presentation about the assessment dashboard, Arizona's assessment dashboard. Okay, so my name is Lucas Stevens. I'm a policy associate at the Nicholas Institute at Duke, and I'll be your host for our Internet of Water webinar today. Today, we're going to hear about a presentation about the open source software that scientists use at Arizona Department of Environmental Quality to complete their Clean Water Act assessments. The automated process has reduced the amount of time it takes to gather and analyze massive data sets, transforming a task that used to take up to 9 months into one that takes only 15 minutes. So we're going to hear from Jason Jones, a senior scientist at Arizona DEQ. And he's going to walk us through the software and demonstrate Arizona's publicly accessible dashboard.
Thank you very much, and hello everyone. I'm very excited to talk with all of you today about Arizona's assessment dashboard. So this is a publicly accessible tool that we developed using open source software to show which lakes and streams throughout Arizona are either impaired or meeting standards. So today's talk is going to be in 3 parts. I'll start with a little bit of background, and then I'll show you how I used a program called R to develop the assessment dashboard. And then we'll end up with kind of the resources and training that were used to develop the application. So let's start with some background. What is a water quality assessment? So an assessment determines if standards are being met for each designated use and for each water body. And designated uses are different for each state. And in Arizona, we have designated uses for domestic water source or drinking water, recreation, fish consumption, irrigation, livestock, and aquatic and wildlife. The important thing to kind of keep in mind here is that a parameter or standard like pH can straddle multiple uses. So you might have different standards for one parameter for each of these different uses. So states are required by the Clean Water Act to submit an assessment of water quality every even year by April 1st. These are the 22 assessments that Arizona has done since the Clean Water Act was established back 50 years ago. And states really have recently started to struggle with completing their Clean Water Act assessments because of the increasing complexity of gathering and analyzing massive data sets. So for Arizona, it has been about 20 years since we've actually submitted an assessment on time. Nationally, only about 7% of states and territories submitted their 2020 assessment before the April 1st deadline. So that's not great. That is kind of a sign of a broken process. So what is so hard? In 2013, EPA surveyed states for which parts of the assessment process that states found the most difficult. The items here in red are more technical in nature, while those in gray are more administrative. States found that gathering data, formatting that data, and creating and finalizing the actual assessment report were the top 3 things that took the most effort. Today's presentation will show how Arizona basically automated everything in red, essentially zeroing these things out. Now, I should point out that Arizona did not submit our 2022 assessment by the April 1st deadline. We actually submitted it on April 5th. So close, but not quite. These administrative tasks still were obstacles for us to submit on time. So this slide kind of shows the way we used to do things versus how we are doing things now. So we used to import other agencies' data like the USGS into our database and then reformat that to match things like parameter names and method types. So it took us about 3 months just to go out and gather data from all the different sources, be it in spreadsheet formats or PDFs or actual databases. And then in about another 6 months to format that data so that it could match the schema in our database. So that's 9 months of time just to begin assessing data for the first time. So we had a broken tool that a contractor developed for us that took another 4 months of data wrangling to produce our assessment files and 800-page report that we would then send off to EPA. And EPA's database that kind of houses all the different assessment decisions is called attainments. So overall, we're looking at 13 months of time to do one assessment. So we definitely were looking for ways to speed things up. And this is where the water quality portal comes in. So the water quality portal is where the nation stores our water quality data. So it's got a really easy to remember website. It's waterqualitydata.us. And if you haven't been on it, definitely check it out. The key point here is that the portal has the data in a common schema, and that drastically improves how we can get data and access it. So to get an entire cycle, assessment cycle worth of data for Arizona, for instance, takes about 7 minutes. So I then wrote R code that aggregates the data and compares it to standards to make parameter use and water body decisions that we then send off to EPA. So that process takes another 5 minutes. So we're looking at around 12 minutes versus 13 months. So that is really an extreme improvement in time. But why does that matter? A little bit later in the talk, we'll go over the assessment dashboard, and that dashboard requires relevant and timely information to be useful. And the best analogy I can think of to kind of explain this is imagine going to a grocery store with a list that is a year or two out of date. That is essentially what we were doing under this old approach, where it took us over a year just to process that information. So we were going to places throughout the state where other agencies like USGS had already monitored, and we just didn't know it. So we were wasting time and money doing redundant sampling. So let's talk a little bit about water quality infrastructure. So the water quality portal is our main source of water quality data. About half the data we use in any given assessment is from about 30 different groups, some of which are pictured here. We use a program called R to take that raw data and turn it into decisions like attaining or impaired. So at this point, I'd like to ask kind of a poll question. So David, if you could fire up our poll question, get a sense in the audience of, I'd like to know what kind of programs you guys primarily use to analyze data. So you should see it on your screen. So we'll take a couple of minutes to give you time to answer that question. All right. Awesome. So hopefully you can all see the results here. So looks like most of you answered that Excel is the primary thing you use to analyze data, which I still use Excel frequently. It's kind of the go-to, the answer, questions, kind of in a spreadsheet format. And then number two, we've got R and Python with, 38 of folks out of 75. Then we've got SQL and some of the more, the other types of programs. So that's really awesome. Thank you for participating in that. We're going to talk, get control back here, about a program called R. So what is R? For our purposes, today we're going to say that R is a programming language that allows users basically to string together commands. So R is a free and open source program with a really great user base. And for our purposes, think about it like a data factory. So Excel is really good at kind of answering specific questions and getting more simple answers to things. R is more about automating a process. So just like a factory where you have kind of a conveyor belt and you might want to filter some data, add a column, join it to another table, and do things in sequence. So this kind of spaghetti-like diagram shows the inputs and outputs for an assessment. So on the input side of things, we have water quality data from the portal. Then we have assessment units, which are things like stream reaches or lakes, standards, previous decisions like impairment decisions carry forward, impairment or attainment logic. And that's things like how many exceedances do you need of a standard before you call it impaired? And then out of the funnel come decisions at the parameter use and assessment or water body level. So for example, we can say that if a stream didn't meet criteria for arsenic, then we would say that the aquatic and wildlife use is not supporting and the entire water body is impaired. So the next thing we're going to do is kind of take you on a tour of, do a demonstration of R code and a Shiny Flex dashboard application. So the R code is kind of the engine that makes everything work. So it's where all the math happens and is really integral to how getting those actual decisions. The Shiny dashboard is for people who aren't programmers and aren't developers and allows them to actually interact with the data. So with that, we're gonna hop over here. So this is RStudio Pro. So this is not the free version, but it is totally optional. You could actually run this with the non-pro version, but the pro version is faster because it runs on a dedicated server and it allows for more collaboration. So RStudio is a development environment. This is our data factory. So within here are about 5,000 lines of code that makes this work. And in like word processing terms, that's like 130 pages or so. So that gives you a sense of the scope of the math problem we're trying to solve. The goal for this part of the demonstration is to show you how the factory works. So you won't be an expert in the 10 minutes that I'm going to demonstrate this, but I hope you get an understanding for how the code works to automate a process. So little orientation. RStudio has 4 default panes, and this one is called the scripting pane and is where the code lives. And here we have the environment pane, which is already populated with different data frames and tables because I ran it before the presentation. I want to draw your attention to the GitHub tab, which is kind of like Word's track changes. So you can basically see what has been changed in the code, and then there's a process to promote that to production. And then down here, we have the console, which is where the code is run, and then kind of the file structure here, which is similar to Windows Explorer. So all the code that we'll be kind of walking through today has kind of an A to Z type suffix or prefix. So that will kind of help guide you through the different 5,000-ish lines of code. So if you see the letter A, you're in the kind of gathering data part of the code. Letter F is for comparing results to standards. Just kind of puts everything in its own little module. We're going to open up the A load data from EPA to kind of see how we get data from the water quality portal. So here at line 104, we have a bit of code that you can see there's a website for the portal, and the way the water quality portal works is through something called web services. So it essentially is through a URL, you can basically put an order in for the kind of data you want, and it'll spit out a zip file with a CSV with your data. So we're going to tell it within the URL that we want data from this state, which is the code for Arizona. We want data for lakes, impoundments, and streams, and we can define what date range we want for the data. So when we run that, we get a data frame that is about 200,000-ish records and 31 different columns. One of the things I really like about RStudio is that it's more visual than other development environments that I've seen. So you can click on a data frame and see exactly what that looks like. So we can see we have data from the USGS. We can look and see what kind of data that is. So we have things like temperature and oxygen and pH and the results here. So this is the raw data from the portal. Things that you won't see here yet are things like, what are the standards associated with each of these parameters, or, show me the data in a common unit or aggregate that data. So all those things are future steps in the pipeline that need to happen before we can get to a decision at the water body level. So the next thing I kind of like to go over with you is kind of in the compare results to standards part of the code. So we're going to run together this block of code. And I'll just draw your attention to line 49, which has this pound symbol, which basically means that it's a comment, a human comment to explain the machine code that's going to be following. So the more comments, the easier it is for someone who didn't write the code to understand it. So this is telling us that this is a regular standard. So it kind of implies that there are non-regular standards. So we have F1 here that we're going to go over together, but just the kind of point out there are other types of standards like oxygen, which aren't what I would call the bright line standards. So oxygen, for instance, you need to know the concentration and the percent saturation. And we have other types of standards like hardness dependent standards, or suspended sediment concentration, or ammonia. So lots of different flavors of standards, but we're going to go over just the regular standards together. These are also the most common standards throughout the state. So I know for some of you, coding can be somewhat terrifying, and then for others of you, it could be super thrilling. So for those who might be terrified, I want to try to dispel that. So a lot of us have taken, say, an average in Excel. If you've done that, you'll have a function average, and then in parentheses, you've got different arguments. R works basically in the same fashion. So we have a function called filter, which does exactly what you think it would do. It's going to filter this input, this data frame called F standard type join. So this is data that's been aggregated and formatted. And then it's going to look for this column called standard type and just look for the ones that say regular. So let's see how that works. So we see the F standard type join, the table that we're going to use as an input has about 434,000-ish records. I'm going to open that up and kind of take a look. So since we started out kind of looking at the raw data from the portal, and some things have been done to it since then, you can see we have this water body ID, which is basically the reach or lake that uniquely identifies that water body. We've aggregated the dates, so you don't want to, if you sampled 100 times on May 7th, you don't want to treat that the same as other dates. So it's important to aggregate. The characteristic name and the sample fraction are the same as in the raw data, but we now have designated uses associated. So you can see different uses like domestic water source or irrigation. Then we have the result, and then lastly, the standard type, which are the different flavors of standards. So we can kind of take a quick peek at how many regular standards we think there should be. And filtering it down, we can see, all right, there's about 71,000 records. But we didn't actually run the code. We're just kind of interactively, using RStudio to kind of look at the data. So actually running the code, I'll just hit Control Enter and kind of step through that. We can see, we've got 71,000 records, so that looks good. And now we only see, the standard type regular here. But what we don't have, we've got the result, but we don't have standards. So that is kind of our end goal, is to compare the result to the standard and figure out if it's exceeding or not. So that's our next step. So this line 52-ish to 56 basically tacks on the standards, to the results. So it called it the same data frame, so that didn't change any. So, basically everything from water body ID to the standard type is the same. And then you see we've got some new columns. So we now have the standard here in the same units as the result. And what we need to do next is answer the question, is this result, greater than or not from the standard. So that happens here. And I'll just kind of walk you through what this means in English. So mutate is a function that adds a new column. And that new column is going to be called exceed. And if the result is greater than the standard, it's going to put a yes. And if not, it'll put a no. So if you can kind of keep your eye on the number of variables here at 15 at the moment, we're going to run it. And you can see it increased by 1 by adding that exceed column. So there it is. And maybe we're interested in, all those that actually do exceed. So we can kind of filter it down for the yeses. And, take a look at this very first row is for selenium. And we can see, the result is 0.0021 and the standard is 0.002. So that kind of makes sense that it is flagged as exceeds. Okay, so that was kind of the, we kind of went as a group together through, a dozen or so lines of code. The process to get to the end is basically the same. You're just kind of stepping through all 5,000 lines of code to get to, is it impaired or is it, attaining? The next thing we're going to kind of demonstrate is the actual assessment dashboard. So this is a R Shiny Flex dashboard application. So what does that mean? So these are basically packages that build you an HTML web page using code that the user provides. So the app opens on this dashboard screen, which shows summary information about the current assessment. So this disclaimer is pretty important. Basically is saying that this is provisional until EPA approves the official assessment. And then gives, this is basically an active assessment. It ends on June 30th of this year. The code is run, we run this every week. So you can see it was last run on Monday. And then you get a sense of like how many records, how many impairments, how many exceedances there are. And then it breaks down, everything basically at the parameter use and water body level. So kind of like a baseball box score of assessment information. Maps are super helpful. So this is a kind of an aerial view of all the different water body decisions throughout the state. So red is impaired, green is attaining or healthy, and then yellow is inconclusive. So we kind of hover over this particular reach. This is the verde, and then you see the parentheses after it. That is the water body ID. So think of a water body ID like your home address. If we didn't use that, we have streams like Sycamore Creek, which I think there's 8 or 10 of those throughout the state. We need a way to uniquely identify each water body. So throughout the document, it is set up as a web page, so you can navigate by just clicking different buttons. This README file has kind of how the document is set up and what some of the field names and terminology mean. Basically a standard operating procedure for how to use the application. The impairments tab gives you our current number of impairments as of this week, but also what we're kind of measuring against, which is the last official decision, which here is back in 2018. the impairment causes will kind of show you a graph of all the different impairments throughout the state. For some reason, it's taken a second, but impairment causes throughout the state. So you can see that we have 51 impairments for E. coli, 49 for copper, and 30 for mercury. So it gives you a quick look at what causes impairments in Arizona. But now the fun part. So the main point of this application is to show our work behind assessment decisions. So the decisions tab, gets at the question, how did you actually make a decision at every level? So when you open up this tab, you can see these subtabs, which let you drill into and out of the data. We're going to look at a couple of different examples. Before we do that, we'll just take a quick peek at how many sycamore creeks we actually do have, which looks like 8. But we're going to look at the Colorado River. And this is going to be an impairment example. And then the next example we'll go through is kind of a healthy or attainment example. So we're going to look at the Colorado River from the main canal in Yuma down to the Mexico border. This is the water body ID that uniquely identifies it. If we put that into the selection criteria here, we can then see that this section of the Colorado River is impaired. And all the other uses are supporting, but aquatic and wildlife is not. And if you need to know what the acronyms mean, you can always go back to the README file here, and it kind of walks you through that. We're interested in why is aquatic and wildlife not supporting. So we can keep drilling down. I will point out that most states kind of stop here, and this is where Arizona used to stop. We never gave details on how we came about that a use was fully supporting. That was kind of beyond us at a technological level. But this assessment dashboard lets you kind of drill in down to the parameter level, and we can see that the aquatic and wildlife use is not meeting criteria because dissolved oxygen has 13 exceedances out of 71 total samples. And it's also exceeding for 3 samples out of 38 for selenium. So that part is huge, knowing the number of exceedances and number of samples backs up your final assessment decision. But we can go even further down the rabbit hole. So if we want to know the kind of sample by sample comparison, where we're looking at what is the standard and what is the result for each decision, we can click on the exceedance tab and see that it has 3 selenium exceedances, and that standard is that kind of bright line standard that we walk through together. But it also kind of details out those more complicated standards like dissolved oxygen. It'll show you what the % saturation that was used and the result. So that's pretty powerful. If we wanted to, we could actually go to the basement level and see the raw data. So this is not aggregated, not formatted in any way. This is raw from the water quality portal. So that was our kind of impairment example. Let's look at a attainment example, which ironically is a stream called Devil's Chasm Creek. And that one is attaining because each of its uses is fully supporting. Clicking on the parameter tab, I'll draw your attention to this field called core, which stands for core parameters. So for full use support decisions, core parameters are the minimum parameters needed in order to make a full use support decision. So we can see that for all these different core parameters, you're not only meeting criteria, but there are no exceedances present at Devil's Chasm. So, all right, the last thing I wanted to show you was an inconclusive decision. So that one will be the Verde River. That one is here. So it is inconclusive because we don't have enough information for most of the uses. So it only has one use, full body contact, that is supporting. And we can see the data here, but what we're missing is what additional information would be needed to, say, turn boron for the irrigation use to either meeting criteria or not meeting criteria. So for that information, we need to go to the Data Gaps tab. So the Data Gaps tab answers the question, if you have an inconclusive, what additional information is needed in order to flip that decision to either attainment or impairment. So this is the project map kind of sub-tab, which shows every inconclusive that we currently have in the state, and what forces we have basically deployed the sample. So you can see here we've got USGS, who is actually currently down in the Grand Canyon sampling all these sites. The purple are volunteers, so we use a lot of volunteer data in our assessment, and you can kind of see how active they are throughout the state. And then the gray dots are basically unclaimed, inconclusive decisions around the state. So that's really important to identify places where no one's actively looking at them. So we're interested in that Verde site. So we'll scroll down here, and under the Data Gap Summary tab, we get basically a grocery list of what we need specifically to flip that decision. So this one needs one total boron, and it gives you the actual months the sample for, because to make a attainment decision in Arizona, they're seasonal dependent. So you need to have seasonal distribution in order to make that decision. So one boron, one copper, down the list. So this gives us basically surgical strike abilities in sampling. And for our agency, this one feature saved us about $500,000 in sampling cost. So instead of sampling the old way that we used to do things, where we would sample for everything because we weren't sure, what we actually needed, we can, cherry pick and, attack just the things that we actually need, and that is huge. The last thing I just wanted to show you, just in terms of transparency and reproducible code, is the source codes, for the applications, directly available through clicking that button there. All right, so the last thing I wanted to talk about was resources and training. So, I showed you this tool that is really cutting edge for the nation at the moment, that takes data from the water quality portal and then transforms that into decisions that we can then serve up to EPA. But how did we actually do that? We're not like the movies. We don't have a cast of thousands, and we don't have a budget of hundreds of millions of dollars. For this version of the tool, it's really two of us. So I'm the assessment lead, so I know how all the logic and the business process works. But I'm also the developer. So I wrote the code that kind of takes us through all the steps. So it's an added bonus to have someone who knows both of those things. Glenn Holroyd is in our IT department. He basically is the architect behind things like setting up the server and RStudio Pro. We're using Amazon Web Services for a serverless architecture type environment. There's fancy things he needs to do to make that work. He is a huge help in kind of QCing the code, so that GitHub process, so that we have a approval of when I do make changes, that we have a second set of eyes kind of making sure that it makes sense. So, I wasn't originally a R developer, but I am now. I started to learn R when I saw states like South Carolina and New Jersey automate parts of their assessments using R. I taught myself R primarily through a website called DataCamp. Now, there's lots of other training resources out there, but this is the one that worked well for me because I liked the interactive kind of problem solving. So they'll give you a problem and then you write code to kind of get to a solution, and that worked out pretty well. For the code that I kind of demonstrated today, these 5 courses kind of, basically are the key to understanding that bit of code. So the Introduction to R course, Intermediate R, Data Manipulation with dplyr, which is a package in the tidyverse, joining data with dplyr, and building dashboards with Flex dashboards are like the main courses to kind of, if you were going to go down this road, those are the ones I would definitely suggest taking a look at. DataCamp's pretty cheap. It's like $300 per person per year, so a pretty minimal investment in the greater scheme of things. All right, so wrapping up, we've covered a lot of information here today. I think one of the things I wanted to stress was, we went over an example that's specific to Arizona, using the portal and R, but it's definitely much broader than that. So I know we have a lot of different diverse backgrounds here on the call today. So I just want to stress that to me, R is kind of like Legos, where you kind of start out with a jumbled mess and you can really build anything you want. So it's flexible in terms of, basically whatever problem you're trying to solve, it's a powerful tool to get you there. So with that philosophical advice, our code is available on GitHub, so you can definitely check it out here at the address below, and then our dashboard is publicly accessible. You can either go to the AZDEQ website and navigate there, or go directly through this link. So with that, I will happily take any questions you guys might have.
Great, thanks so much, Jason. So we have a number of questions already coming in. Some of them you've already answered, but I'll just start at the top in the order that they came in. So what kind of supporting documentation do you provide to EPA and other stakeholders on impairments?
Yeah, so EPA has a lot of different requirements specific to impairments, and they want to see, basically all that kind of background information, like, not only the raw data, but the, how we got to each decision. So, showing the number of samples and number of exceedances, showing that, we, ensured that the data is credible. So there's a bunch of steps in, quality assurance and quality control that just make sure that the data we're using runs through some basic, processes. Volunteer data is always under scrutiny. So, we do use a lot of volunteer data, but we have a rigorous process to kind of make sure that the data we are using, goes over all those different thresholds.
Great. And so, so another question. So what do you do with all the time that you've saved by this automation? And, you mentioned that you had sort of duplicated some monitoring sites, and you sort of found that out through this process. So has that enabled you to shift around those monitoring sites and sort of extend the amount of monitoring that you're able to do?
Yeah, so for the first question, it is a huge time saver. We basically had a full-time employee doing nothing but formatting data, which wasn't great. So we didn't have to let anybody go or anything. We just repurposed, people's tasks. So, instead of, formatting data, we concentrated more on, upgrading our own internal database and things like that. So we're never short for things to do. Monitoring in particular, there's more streams and lakes to monitor than we will ever have staff and budget to do. For the second question, I think we, we're able to view data in a way that we hadn't previously been able to do. So we used to kind of get old, intelligence reports, about, sample the Verde River, and then you find out that USGS had already sampled it. And so we don't make those mistakes anymore. We're able to kind of be current on, exactly where the sample, and start to leverage, there's a lot of people who want to kind of help out, and we can kind of deploy resources a lot more effectively. So the volunteers are a great one. They really want to help out, and we weren't the best as we could have been at actually giving them, sites and places that kind of close data gaps. So now we're able to kind of say, if you're in the area, these are the things we could really use help collecting. And that's been a great partnership.
Thanks. Okay, so next question. How long did it take you to develop the platform? And if you don't mind sharing, what was the budget?
So the time frame, so we started we had a tool that was kind of Java based that essentially no longer was supported. So we were, kind of forced to develop a tool, and we got that kind of stood up, within 6 months. So actually developing it and starting to use it, it was about a 6-month process. And then it was kind of a plan, do, check, act, cycle where we, kept improving it and adding on to it. It initially didn't have, like, attainment decisions weren't part of it. So it was kind of a iterative process where we, grew it. But the initial push was about 6 months of a lot of time just developing and doing testing to make sure that it was giving us the results we expected. Budget, it's pretty much time. It's just people time. So R is free, but that doesn't mean that it's free in terms of time. So I would say the biggest thing is there is a learning curve for getting up to speed. It's a language, so it's kind of how I think of it, is you have to learn enough to be fluent, and that takes time. So we've invested in me learning R, and just in case I get hit by a bus or something, we've invested in redundancy. So there are junior staff who are now going through part of DataCamp called DataCamp Teams, where we're able to kind of assign courses and make sure people are fluent in the parts that we need to run the tool.
Great. And then we have two questions about data sources. So you were already saying you use volunteer data, and there's a robust QA/QC process. Can you confirm, when is this process? Is it before the data goes into the water quality portal, or after you take it out? Do you only use data from the water quality portal? And if so, do you get pushback from EPA or others about this?
Yeah, so our one and only source is the portal, but that does include about 40 different groups. So it's half the data we get in any assessment is from external providers. And we have a variety of ways that we're trying to help people get data in. So in the assessment world, we're tasked with kind of an unfunded mandate of get all readily available data, and that sounds great, but is data on the back of a napkin or in a PDF readily available? I would argue no. So what we do in order to kind of make sure that we get as much data as we can, humanly possibly get, is every February we issue a call for data and kind of give instructions for how external providers can share that with us and get that available. And that works pretty well. Volunteers don't. We generally have a path through our database for them. For people who struggle with submitting directly to WQX and then the portal, we have an easy button where they give it to us, and we'll go through the extra rigmarole to publish that data.
That's good. And then it looks like the last question here. So what did it take to convince higher up folks that learning R and switching to it is worth it? Because as the question asker says, we're usually risk adverse, especially in government. So what was, how did those conversations go, and how did you convince people to let you spend the time learning R and developing this?
Yeah, so it's a big paradigm shift. So we definitely experienced, lots of hard questions from our IT folks about security, and we're an Oracle shop, so that's what people are mostly familiar with. So there were a couple things that helped walk us through that. One was just showing that states like South Carolina, New Jersey did it. So proof of concept, they were on the cutting edge, and we wanted to kind of be a technical leader as well. So we wanted to kind of follow their footsteps. I think Glenn Holroyd with our IT folks was a great advocate for kind of showing like what it could do, and making it what in their terms was an enterprise level solution. So we had to basically convince our leadership and IT folks that we can develop something that is that will stand the test of time. So and we did that by kind of showing different features of R, like you can basically freeze versioning, so you don't have to worry about getting becoming obsolete as a package or something gets upgraded. Packages like PackRat make that really, really great, and you can make your application last pretty much forever that way.
All right, well, great. Well, thank you so much again, Jason, and thanks for all the attendees for the questions. Do you have any final thoughts for us about the assessment dashboard?
Well, just a parting thought. So there's always things that we're looking to do next. So, I think right now the dashboard and the code are pretty cutting edge, but there's always those things that we love to add. So what isn't shown here that I would love to do someday is, kind of dealing with assessment histories, and, better integrating with EPA has this really great resource called How's My Waterway, which is another great resource that check out if you have the time. But it basically has attainment decisions along with monitoring data and permitting all integrated. So, starting to match those multiple different sources of data and tell a story. So I think love to do that.
All right, well, great. Thanks so much again. And thank you to all of our attendees.